All right, so let's do this. We're going to start in on our new chapter here, chapter 18. The title of chapter 18 is Ionic Solutions. So we're going to be talking about solutions again. We've been talking a lot about acids and bases. That stuff isn't going away. We're going to do a lot with pH in this chapter here as well. Okay. The first topic that we have to cover here for chapter 18 is this topic of buffers. Okay. Or buffer solutions, I guess we can more formally call them. All right, so first of all, what is a buffer? A buffer is a solution that's created with a mixture of a weak acid and its conjugate base. Or you could also have a buffer that was a weak base and its conjugate acid. All right, so these are solutions that you prepare, right? But when you're preparing this solution for it to be a buffer, it's got to be a mixture of a weak acid and its conjugate, or a weak base and its conjugate, right? You mix these two together, you have what we call a buffer solution. All right, and so what is a buffer solution good for? Buffer solutions, they resist changes to pH. All right, so let's say that we have like a beaker of water and we add some strong acid to it. What's going to happen to the pH? Is it going to go up or down? If we put an acid in there, it's going to go down, right? If we instead took that same amount of strong acid and put it into a buffered solution, its pH would drop a little bit, but not very much at all. This buffer's whole job in life is to resist changes to pH, keep the pH relatively constant. Okay, I was a biochemist by training. Every single experiment I ever performed in the lab was taking my protein and putting it in a buffered solution. We work with buffered solutions quite often. Your body likes to be at a very particular pH. If it was anything at any other pH, all your body's chemistry wouldn't work. So how does your body keep that pH constant? It employs a buffer system. Okay, so this is what these buffer systems are doing. They are resisting any changes to pH, and we're going to absolutely go ahead and show this mathematically here in a bit, all right? Let's start on this first part here, this mixture of weak acid and weak base. So for example, we got a bunch of information about weak acids tabulated on our constants page, right? Anything on this list here is a weak acid. So let's just pick one that we've looked at before, hydrofluoric acid. Okay, so if I wanted to make a buffer with hydrofluoric acid, right, I would take a mixture of HF and its conjugate base, the fluoride ion. Right? If I mix these two together, I take a little bit of hydrofluoric acid and then some fluoride ions and mix them together into the same solution, I will have created a buffer. Okay, if I take another acid, so for example, nitric acid and its conjugate, this would not be a buffer. Why is that? What do we consider nitric acid to be? A strong acid, all right? You can't make a buffer with a strong acid. It has to be a weak acid. So this combination would not work. All right? Likewise, I can't just take any random weak acid and any random weak base and mix them together and create a buffer solution. This isn't going to do it either, because these are not conjugate pairs, right? So again, we can't create a buffer with any strong acids or bases. And this mixture that we have has to be conjugate pairs. All right. Cool. So now we're going to create a buffer. We're going to take our hydrofluoric acid and fluoride, and we're going to create this solution. All right, so we created this buffer solution. We made it 0.75 molar hydrofluoric acid and 0.5 molar fluoride ions, right? So a mixture of the acid and its conjugate base. And we want to know, what is the pH? Okay, so we're going to do a similar strategy to what we've done up until this point talking about weak acids. The first thing we're going to do is we're going to build that Ka reaction of HF. Right? From that reaction, we can get that equilibrium expression. And how do we go about solving for these equilibrium expressions? What do? The ice table. All right, so same strategy here. Okay, so take a few minutes, see if you can't get a head start here, and then I'll sort of quietly fill in. All right, so remember when we're talking about our Ka reaction, we're taking that weak acid and we're adding it to water. All right, so here's my acid. Water will be my base. So to get my conjugate base, I'm going to take away a hydrogen and decrease my charge by 1. And then to get my conjugate acid, I'm going to add a hydrogen and increase the charge by 1. All right, my Ka expression, products over reactants. All right, but I'm not going to include water because water is a pure liquid. So I'm going to build my ice table. right? So the big difference here between this type of problem and the type of weak acid problem that we were doing before is that now I have an initial concentration of my weak acid, the 0.75 molar, but I also have an initial concentration on the product side as well of my fluoride ion, right? So that's really the only difference up until now is I'm actually starting with some of this fluoride ion in my solution at the beginning. Right? And to be clear, this is just what was given to me in my problem. My problem said that there was 0.75 molar HF and 0.5 molar fluoride. All right, so that's what I'm starting out with in these two solutions. What's going to go in the change box for HF? Minus X. And what about for the other two? Plus X. All right, and then I'm just going to sum it all together for my E box. All right. So then I can take this and plug this back into my equilibrium expression. My equilibrium concentration of HF, that's that term. My equilibrium concentration of fluoride, that's that term. And my equilibrium concentration of hydronium, that's that term. So we get Ka equals 0.50 plus X All right, so here's what we get using the same strategy that we've used up until this point for getting pHs of weak acids. All right, we're going to take this and we're going to do some algebra with it because then we're going to get this relationship that we're going to be able to use in each problem going forward. That's going to make our lives a little bit easier so we don't have to do an ICE table every time. All right, so we're just going to do some algebra with this relationship right here. What is it ultimately in this that I care about? Like, what am I looking to find if I want the pH of this solution? X, right? Because that is my hydronium ion concentration. That's what I'm really after here, that hydronium ion concentration. So I'm going to go ahead and put that hydronium ion concentration in for X as a variable, and we're going to solve for that. All right, we're just going to do some algebra, rearrange, solve for that hydronium ion concentration, because that's what I want, right? That's what I'm after in these problems. So in order to do that, I got to multiply both sides by that 0.75 minus X, and divide both sides by that 0.5 plus X. All right, and now we're going to get to make a simplifying assumption here that's going to make our algebra a lot easier. All right, if we go and we look up that value for Ka, we see that it's a small number, right? A reaction that doesn't really, that actually strongly favors the reactant side, right? So there's not very much reaction that was going to happen. This is the same argument that we made before when we were talking about weak acids. And now it's even more true than it was before, because at least when I was doing weak acids, I was adding only to my reactant side, right? So the Chatelier's principle, that pushes stuff towards the products. Now I'm adding to both sides of this reaction. I'm adding both reactant and product. So there's very little like reaction that's going to happen here. So bottom line is we get to make that same assumption that X is super small, which means that 0.75 minus X is basically just 0.75, and 0.5 plus X is basically just 0.5. All right, so now I have this simplified relationship here. I'm going to leave these still as their values. We'll see why here in a second. All right. And then finally, I don't just want the concentration of the hydronium ions, I want the pH. So what am I going to do to that concentration? Negative log, right? And so we're going to do, anytime we can do an algebra, we can do anything we want to one side as long as we do it to the other side as well. So I'm going to take the negative log of both sides of this equation. All right. On my left-hand side here, this is just the pH, right? That's the definition of pH. On my right-hand side, I'm going to do some more algebra. That multiplication problem within that log term, I can separate that out. That will become an addition problem in the magical world of logarithms. All right, and now we're going to define a new term here. The negative log of the concentration of hydronium, we call that pH. The negative log of the concentration of hydroxide, we call that POH. The negative log of a Ka, we call the pKa. All right, and then lastly, within this term right here, I can get rid of that negative sign. This is another just log algebra thing. You can trust me on it if you don't remember your log algebra. I can get rid of that negative sign if I flip that fraction, right? So the negative log of 0.75 divided by 0.5 is the same thing as the positive log of 0.5 divided by 0.75. And just plugging back in what those variables were, that 0.5 was my concentration of fluoride, my conjugate base, and my 0.75, that was my concentration of my acid, my hydrofluoric acid. All right, so using that Ka expression and that ice table, that same strategy that we did before, we've kind of arrived at this formula here. This is what's called the Henderson-hasselbalch equation. All right, and anytime we have a buffered solution, we can use this equation here. All right, so this Henderson-hasselbalch equation is specific to buffered solutions. So from here on out, when we want to calculate the pH of a buffered solution, we don't have to do it the long way. We can just use this equation right here. All right, so then finishing this off here, I'm going to need to look up my Ka for this particular acid and conjugate base. All right, that's that 6.8 times 10 to the negative 4. And since it's the pKa, I'm going to take the negative log of 6.8 times 10 to the negative 4. And then add the log of the concentration of my base. My fluoride ion had a concentration of 0.50 molar. My acid My hydrofluoric acid had a concentration of 0.75. All right, so negative log. Oops. All right, so I punch that into my calculator. I get 2.99. That is the pH of my buffered solution here. Okay, so if we're trying to calculate the pH of a buffer, we can use this Henderson-hasselbalch relationship here. To make our lives a little easier. All right. So now we want to show mathematically here, using some calculations, that our buffered solutions do indeed do what buffer solutions are supposed to do, which is resist changes to pH. Right? So we're going to illustrate that by doing a few calculations. Okay? So first, let's do one so we can compare here. What is the pH of a 0.1 molar solution of a strong acid like hydrochloric acid? So everybody take a second. We should remember from our acids and bases chapter how we can take the pH of a solution of strong acid like hydrochloric acid. All right, remember strong acids are kind of like best case scenario because since that acid is strong, 100% of it will dissociate, which means that I get to say whatever my concentration of strong acid is, that's going to be my concentration of hydronium. So my concentration of HCl in this problem is the 0.1 molar. So that's going to be my hydronium ion concentration. And once I have that hydronium ion concentration, I can just plug that in, take the negative log. So the negative log of 0.1 is 1. All right, so for strong acids, we get to say that the concentration of strong acid is the concentration of hydronium. So we take the pH of that concentration of hydronium, and we get our pH of 1. Okay, and so if I'm making a solution of hydrochloric acid, I added this to water. What was the pH of that water before I added it? 7. Right? So this solution went from 7 down to 1. All right, so 6 pH units drop right there. So now we're going to do the same thing. We're going to take this same amount of acid, but we're going to add it to a buffered solution. All right, so now let's create a buffer solution. For the sake of variety, what we're going to do is we're going to choose one of our weak bases. We'll do ammonia. Okay. So we're going to prepare a buffer. Using 0.67 molar. All right, what would be the everybody take a second and give me the formula for the other molecule that I'm going to use to make this buffer here. All right, if NH3 is my base, what's my conjugate acid going to be? What's our conjugate pairs here? All right, so if it's a base, it's going to accept a proton, so it's going to go up in the number of hydrogens, so NH4 and up in charge. So these two together, I could make a buffered solution with. Ammonia and ammonium is what we call the ion. All right, and let's figure out what the pH of this buffered solution is before we get started. Okay, we can use that new equation that we just derived, that Henderson-hasselbalch equation, which equals the pKa which one's my base? The ammonia, we'll call that A, or the ammonium, we'll call that B. Which one's my base in my log that I'm going to do here? A or B? A. So A is going to be the base form. B is got that extra proton. It's going to be the acid form. All right, so I can plug those in. My pKa, what am I going to need to do for that one? Where do I look? I look on my table. But if I look, I don't find ammonium anywhere on this table. I can't find the Ka of that NH4+. What I have is the Kb of my ammonia. All right, and so how can I use that? Right, we have that relationship for conjugate pairs between their Ka and their Kb. The product, Ka times Kb, is always that same magic number, the Kw, which is 10 to the negative 14. All right, so if I rearrange this equation here, I can find my Ka by dividing 10 to the negative 14 by my Kb. Again, the Kb I get from my table here. In this case, it's 1.76 times 10 to the negative 5. Oops. All right, so 5.68 times 10 to the negative 10. All right, I need my Ka for my Henderson-hasselbalch equation. I couldn't find my Ka for my acid on my chart, but I had the Kb, right, for my conjugate pair here. So I can always find the one that's missing as long as we're talking about conjugate pairs. Cool. All right. So then going back, now I have a Ka to use. So I'm going to take the negative log of that value. Plus the log of that acid to base rate, or base to acid ratio. Okay, plugging that in. All right, we get a pH of 9.32. All right, so I've made this buffer solution with ammonia and ammonium. I got a pH of 9.32. And again, we're going to sort of prove here that this buffered solution is more resistant to changes in pH than just normal water by itself. So we're going to take this buffer and we're going to add that same amount of hydrochloric acid to that 0.1 molar. Okay, so now we're going to say HCl is added 0.1 molar. What is the pH of my solution now? All right, so we talked about how we can get the pH of a buffer solution all by itself, right? Just using that Henderson-hasselbalch equation. We don't even have to do it the long way with the ice table. I mean, we can, but we don't have to, right? We can just use our Henderson-hasselbalch. So now what are we going to do? What's our strategy for when we start adding crap to it, for when we add strong acid here? Well, we got to figure out what our acid is going to be reacting with. There's a mixture in this solution of NH3 and ammonium, right? We need to ask ourselves, which will react with the HCl? All right, so let's remember here in this conjugate pair, which one is the acid? The NH4, the one with the extra proton, right? It's got one extra hydrogen, so that's my acid in this pair. The NH3 is my base in this pair. Checks out because it's on my list of weak bases. So check, check, it's a base, right? So then which one is going to react with the strong acid HCl, the base of the acid? Base, right? Bases react with acids. So when I'm building my chemical reaction here, I'm going to have my HCl plus the base, my ammonia on my reactant side. So if this is my acid and this is my base, take a second and give me my other products of this reaction. All right, so Notice that this is no longer a Ka reaction, right? We're not just adding some water here. We're taking an acid and reacting it with a base. We can still predict our conjugate pairs here. Remember, acids will go down in their number of hydrogens. So this will be the chloride ion, right? Down in number of hydrogens, down in charge. The opposite will happen for my base. It will go up in the number of hydrogens and up in charge. Okay. Now the last thing that's really important, so first of all, the first thing that we had to do was to build that reaction between our buffer and what we added, which was in this case that strong acid. All right, and then the other thing that's really important to note here is that because HCl is considered a strong acid, its conjugate base, the chloride ion, is an absolute trash base, right? The conjugate of something strong is terrible at being a base, so terrible that we consider it neutral. All right, and that's just good news for us because it means regardless of how many chloride ions are produced in this reaction, it's not going to have any effect on our pH. We really don't care about the chloride ions. All right, so step one, we had our chemical equation that we had to build. All right, step two is usually to build this like equilibrium expression, but in this case, because it's a buffered solution, we're going to get to use that Henderson-hasselbalch equation. All right, so we'll come back to that here in a second, but we're going to skip that equilibrium expression and just jump straight into building an ice table for this reaction. All right, so everybody take a second. Given our problem here, got to go all the way back to our beginning concentrations as well. Fill in this ice table. All right, so because I'm starting out with a buffer solution, I have an initial concentration of my ammonia and my ammonium. Okay, but now I've also added that hydrochloric acid, so I also have an initial concentration of 0.1 molar HCl in there. We don't have any of our chloride ions to start out with because we haven't had any reaction yet. All right, what's going to be in the change box for my reactant side? -x, -x, and then on my product side, plus X plus X. Okay. All right, so then the last thing that we're going to need in order to solve our ice table here is we're going to use one really important fact here. All of that strong acid that we add gets consumed in this reaction. Right? It's a strong acid. It's going to dissociate 100%. So every bit of HCl that you added is going to react in this reaction here. All right, so why does that help us out? Because that means that we know what X is. X is going to be that 0.1, our concentration of HCl, because again, all of it gets consumed. So I can go back into our ice table here and update. I know what X is, so I'm going to plug in for X. That's 0.1. And importantly, it's 0.1 for all of them, right? Because if I can't have more base reacted than I have acid present, right? So if 0.1 moles of my HCl react, it's going to react with 0.1 moles of base. So then at equilibrium here, I don't have any HCl left over. It all got used up. I'm left with 0.57 moles of my base. I got 0.1 moles of chloride in there, but I don't even really care because it's chloride and it's not going to infect my pH at all. And then I have 0.67 moles of my conjugate acid. Right? So every bit of that HCl that we added has reacted with base and formed our conjugate acid. So my HCl concentration goes down to 0 because it all got reacted. My base concentration decreases by that same amount, so my base goes from 0.67 to 0.57. When this reaction occurs, it makes more of my conjugate acid. So my conjugate acid concentration increases from 0.57 to 0.67. Okay? And again, we were able to fill out this ice table using the fact that HCl is a strong acid, and so all of that strong acid was going to be consumed in this reaction. That's what we used to fill in, to solve for X here. So now I'm left with just a solution of weak base and its conjugate acid, because I don't care about the chloride, and since I have that weak base and conjugate acid mixture, this is just a buffer. Yeah, so I can use my Henderson-hasselbalch. All right, so everybody take a second and tell me what the pH of this solution is. Right, remember we solved for that Ka above. All right, so remember we solved for the Ka of this conjugate pair using the Kb of ammonia rather. And then now we have to take the log of the base over the acid. Cool. And I get a pH equal to 9.18. Okay. So what do we just show here? Let's summarize what we just did with these calculations here. We said that if we have water alone, our pH is 7. And then if we add 0.1 molar HCl, my pH drops to 1. Then we did a calculation with the buffer. With our buffer alone, we had a pH of 9.32. That was what we calculated up here for our buffer alone. All right, and then we did another calculation after we added that HCl. And after we add HCl to 0.1 molar, our pH has dropped, but only to 9.18. Right, so we're adding the same amount of acid in both of these cases. If we add it to water, we get a pH drop of 6 pH units. If we add it to this buffer solution, what are we at? 0.14 or something like that, right? Dramatic difference in how much that pH drops. It still drops. It still drops because you're adding strong acid, but way less than it would otherwise. Okay, so again, the whole point that we just proved is that buffers resist changes to pH. All right, that's what a buffer's doing. All right. So now let's sort of just imagine here. Up here we said that we were going to add 0.1 molar HCl. And the first thing that we had to do was to build that chemical reaction of HCl reacting with our buffer solution, right? So now let's say instead of adding HCl, I'm going to add a strong base like sodium hydroxide. We'll keep that same buffer. I want everybody to take a second and build that chemical reaction between our buffer and now that strong base sodium hydroxide that we've added. All right, so what's important to remember here is, again, in my conjugate pair, what's my acid and what's my base, right? My ammonia was the base. My ammonium was my conjugate acid, right? It has more hydrogens, okay? So if I'm adding a strong base like sodium hydroxide, it's not going to react with the base, with the NH3. Sodium hydroxide will react with the ammonium ion. All right. So my conjugate base here will be that ammonia. All right, what's my conjugate acid? Okay, I'll give you a hint here. Really, looking at sodium hydroxide like this is a little deceptive because this will immediately dissociate in solution to sodium ions and hydroxide ions, and the hydroxide is really the base part, right? The sodium, your metal in your strong base, is not doing a dang thing. It is floating around in solution, it's watching everything go down, it is not participating in that reaction whatsoever. Sodium, not involved in the reaction here. It's just kind of floating around in this solution. So my base is really that hydroxide ion, and when that reacts with ammonium, it will produce water. And to keep things balanced, I'll put my sodium ion over here as well. And then, similar to before, because this is considered a strong base, its conjugates will be neutral, and I don't really care about how much sodium ion or water is produced. All right? But importantly, what I wanted to show was that when you add a strong base like sodium hydroxide, it's going to react with the acid component of your buffer, where if we look back at the chemical equation that we built for adding our HCl, it was reacting with the base component of the buffer, right? So your starting chemical equation will be different depending on whether you're adding acid or base, because acid will react with the base in the buffer, base will react with the acid in the buffer. All right, so that very first step where you build your reaction will be a little bit different depending on what we're adding. All right, so then the last thing that we want to cover about buffers here is that buffers are not exactly like perfect at every single ratio here. They only work within this limited range, what we call the effective buffer capacity. Okay, we saw that that ratio of your concentration of base to acid, this was an important term in our Henderson-hasselbalch equation. Okay? In order for a buffer to be any good at resisting pH changes, this concentration ratio has to be within a certain range here. All right, you have to have a ratio of at least 0.1, but it's got to be less than 10. All right, so you got to have your limits are having 10 times more base than acid or 10 times more acid than base. If you have 100 times more base than acid, it's not going to work very well as a buffer, right? That ratio has to be within this specific range here for this to be any good at doing what buffers do and resist changes to pH. Okay, if we punch this into our Henderson-hasselbalch equation, pH equals pKa plus the log of that same ratio. Let's punch in our limits here. What is the log of 0.1? Somebody bust out a calculator, tell me. Yeah, log of 0.1, and then what's the log of 10? So the positive log of 0.1 is -1, right? Not the negative log in this equation. So the log of 0.1 is -1, and what's the log of 10? +1, all right? So our effective buffer capacity, we can either define that in terms of this ratio here, or just say that the pH has to equal the pKa plus or minus 1 unit, right? So a buffer is most effective when the pH of that solution is right around the pKa of that buffer. If it's outside more than 1 unit greater or less than, it's not going to work as a buffer. All right, so again, we have these sort of restrictions on what we call our effective buffer capacity here.